Hello guys, welcome to Biochem series. In today's tutorial, I will take you through the principle behind single effect evaporator. I will take you through the operation of a single effect evaporator as well as step-by-step way of solving questions about this particular topic. Please hang around, watch the video to the end, hit the subscribe button to support me, and don't forget to like this video. I appreciate all your support. So let's talk about the design and then the principle of operation of a single effect evaporator system. So a single effect evaporator system is made up of a chamber and it has 2 entry points and then 3 exit points. So let's recall the operation of a simple evaporator system. From a simple evaporator system, the feed enters the evaporator system and then water is removed from the incoming feed and then a concentrated product is produced whilst water also exits the evaporator through different compartments. So in such evaporator systems, the heat that is needed to evaporate the incoming raw material is supplied by burning of a coal or any other heat source just to heat up the system. But with respect to a single effect evaporator system, we specially design this system in such a way that the heat needed to evaporate the incoming feed is supplied by a steam that is also fed into the chamber. So the entry points are meant for both the feed and then the steam. So the feed enters through one compartment and then the steam also enters through the other compartment. And since the steam carries higher temperature, it undergoes condensation inside this chamber. And anytime condensation occurs, heat is rejected or heat is released. So the heat that is released as a result of condensation of the incoming steam is absorbed by the feed. So that steam or that heat rejected by the steam is what we use to evaporate the feed to get a final product and then a vapor. And the steam after condensation, the steam now comes out through another compartment as a saturated liquid. So let's focus on the steam. The steam entered as a saturated vapor, and after condensation, it came out from different chamber as a saturated liquid. So for saturated steam and a saturated liquid, they both have the same temperature, just that there is just a change of states. There is just a change of states of the steam from gaseous state to liquid state, but the temperature remains the same. And for the feed, we know that when the feed enters the evaporator, it was already having higher amount of moisture or higher amount of water in it, and after it absorbs the heat that was rejected by the steam, it then undergoes evaporation. And at the end of the evaporation, the water removed from the feed would exit the chamber through the upper compartment there, and then the concentrated products would then exit the chamber through the downward compartment. So this is just the basic principle behind the operation of a single effect evaporator system. The feed and then the steam enters, and then the steam would supply the heat needed for the evaporation of the feed. And at the end of that, the saturated concentrated product would exit the chamber through the down compartment, and then the water that was removed from the feed would then exit through the upper compartment, and then the condensed steam, which is now a saturated liquid, would also exit the chamber through a different compartment. So this is how it works. Now let's get familiar with certain things that would help us with our calculation. So for the feed that is entering the evaporator's chamber, it comes with its own internal temperature that is giving us TF. And then the XF here represents the percentage of solids that is present in the feed. So if you are working with maybe sugar cane, we can consider the percentage of solids in it. If you are working with tomato raw material, we have concentration of solids, or the percentage of solids in the raw material, and then etc. Whatever raw material that you are using, we have fraction, or we have percentage of solids in it, and then we have concentration, or the remaining fractions that is meant for the water in it. And then the HF here represents the enthalpy. Enthalpy just means the total heat content. So the feed enters by having its own total heat content. And also when we check the incoming steam has its own temperature, and then it has its own total heat content, giving us what HS. So the HS here represents the enthalpy or the total heat content of the saturated steam or the saturated vapor that is entering the evaporator chamber. And also for the saturated liquid, it has its own temperature S. Now, the temperature of the incoming steam is always equal to the temperature of the saturated liquid. This is because changes in temperature is not taking place, but changes of phase is rather taking place. The steam is undergoing condensation at a particular temperature. So it is just changing state from gaseous or vapor state to a liquid water state, but the temperature remains the same. That is why TS is the same as what? The TS for the saturated liquid. And then the HS here, the small h, small s here, represents the enthalpy. That is the total heat content of the saturated liquid that is exiting the chamber. And now let's look at the vapor. This is literally pure water that is removed from the feed. So when we remove pure water from the feed and then it comes out as a vapor, it will have its own temperature 1. Now this temperature is the same as the temperature inside the chamber. This temperature of the vapor is the same as the temperature inside the evaporator chamber. In some questions, you would not be given the temperature of the vapor, but you always have to take note that the temperature of the vapor is the same as the temperature inside the evaporator chamber. And the YV here represents the percentage of solids that is present in the vapor. We always take YV to be equal to 0 because we assume that the vapor exiting through the upper chamber is made up of pure water with no solids present in it. And now the HV represents the enthalpy or the total heat content of the exiting vapor. And then lastly, let's consider the concentrated liquid product that is exiting through the bottom chamber. So it has its own temperature L, and this temperature L is the same as T1, that is the temperature inside the chamber. So let's always put this in mind, that the temperature of the vapor exiting through the top is the same as the temperature of the saturated liquid or concentrated liquid that is exiting through the bottom chamber. And this is the same as the temperature inside the chamber itself. And now we have XL representing the percentage of solids present in the liquid product. And then HL representing the enthalpy or the total heat content of the concentrated liquid product. So this is what I want you to take note of. This is just definition of some terms that we're gonna meet as we move forward. So take good note of every single thing. Don't get lost. Follow everything step by step as I am moving forward. Now let's learn about how to perform calculations. That is what is relevant to us. When you are given a question, how are you going to approach it? What are the various steps that you can use to solve these questions efficiently without getting them wrong? So the first thing to do is that we have to calculate both mass balance and then energy balance. Both mass and then energy needs to be balanced on the system. Mass needs to be balanced because we know that the feed is entering, like the feed carries its own mass, and as it is entering, it is also exiting as a vapor and then exiting as a concentrated liquid product. So mass is entering and then mass is leaving. So we need to perform balances on the masses. And then energy too needs to be balanced because there is energy at work. There is heat energy at work here. The feed has its own total heat content. The steam also has its own total heat content. And they have their respective temperatures as well. And they are entering this system. And at the end of the day, the vapor, saturated liquid, and then the concentrated liquid products that are exiting are also having their respective total heat content and then their respective temperatures. So energy needs to be balanced on this system. So we will talk about how to perform mass balance and then how to perform energy balance. This is basically what you have to know about the single effect evaporator system. Now let's start with mass balance. So from our prior understanding of mass balance, we perform what we call total balance and then component balance. And total balance, it just means that the sum of the masses that is entering the system should be equal to sum of the masses that is exiting the system. So we need to consider the masses of the feed and then that of the incoming steam, and it should be equal to that of the vapor, the saturated liquid, and then the concentrated liquid product. So all arrows, always put this in mind, that all arrows that is pointing towards the chamber should be equal to all arrows pointing away from the chamber. So from here, we can see that F and then S are pointing towards the chamber. So F and S should be found on one side of the equal sign. And then all the other arrows, that is the vapor, the saturated liquid, and then the concentrated liquid products that are exiting, should be also found on the other side of the equal sign. That is why F plus S is equal to V plus S plus L. So we can see that we have S on both sides of the equal sign. So S will cancel each other, and then we will get F is equal to V plus L. And this becomes our equation 1. And this is our total balance equation. This is pretty simple. Total balance equation will be given as F is equal to V plus L. Normally, I don't memorize these formula in my head. I just look at the chamber and then I just perform the calculations. The most important thing is to learn how to draw the chamber, learn how to represent the information. So when you know how to represent the information, you can just deduce the formula. You don't need to memorize anything. Always put in mind that all arrows pointing towards the chamber should be equal to all arrows pointing away from the chamber. And that is mass balance for you. Now let's perform component balance on solids. From my previous videos, I keep on saying that component balance is just a balance that we perform with respect to a particular component. In other words, we focus on a particular component. Let's say we can perform component balance on solids alone. We can perform component balance on water alone. We focus on one specific component and then we perform balance on that. So if you want to perform component balance, it is just a matter of picking your total balance equation and then multiplying the feed by the respective percentages of the solids in them. So we will multiply the percentage of solids in the feed, and it should be equal to the percentage of solids in the vapor plus the percentage of solids in the liquid product. And that will give us the component balance equation. You just pick it, you pick the total balance equation, and then you multiply each of the various factors by their respective percentages of the components under consideration. So we know that YV, that is the percentage of solids that is present in the vapor exiting through the upper chamber, is always equal to 0. So the equation would now reduce to percentage of solids in the feed to be equal to percentage of solids in the final product. That is XFF should be equal to XLL. In some textbooks, they represent the concentrated product with letter P. Whether letter P or letter L, it is the same thing. What matters is that the equation should have the percentage of solids multiplying that of the feed on one side, and it should be equal to percentage of solids in the product and then multiplied by the flow rate of the product. So this is our second equation, and then we are done with the mass balance. Now let's move on to energy balance. Let's learn about how to get the energy balance. So for the energy balance, we have total energy balance. The total energy balance on the system is just a summation of, or it's just a balance of all the energies at work on the system. So the sum of energies entering the system should be equal to the sum of energies exiting the system. So total heat energy in should be equal to total heat energy out. I singled out heat because the energy at work here is heat energy. So we need to find the total amount of heat entering, and should be equal to total amount of heat that is exiting. For you to get the various amount of heat entering, we just have to multiply the flow rate of the feed by the HF. HF is the enthalpy of the feed. That is the total heat content. Enthalpy just means total heat content. So your feed F multiplied by the total heat content of the feed, that is HF, plus your steam S multiplied by the total heat content in the steam, that is HS, should be equal equal to your vapor V multiplied by the total heat content of the vapor, that is HV, plus your S. This S here represents the saturated steam or saturated liquid, that is acetylene, multiplied by the HS, H small s, that is the total heat content of the saturated liquid, and this plus LHL, that is flow rate of the product, multiplied by the total heat content of the product. So we can see that all arrows pointing towards the system should be equal to all arrows pointing away from the system. The idea here is that the flow rate multiplied by the enthalpy would give you the total heat content, and that is what we use to perform the energy balance. So let's try to rearrange the formula. You can decide to keep the first line in head, and then when you are giving the question, you can just rearrange and then make the factor or like what you need the subjects, and then you are good to go. So we can see that FHF plus S multiplying HS minus HS should be equal to VHV plus LHL. You don't need to memorize this formula. That is what I always keep saying. You don't need to memorize this formula. Always put in mind how to come up with these formulas. Just put this in mind that total energy balance is given as total heat in to be equal to total heat out. And it is obtained by multiplying the various flow rates by the various enthalpies and then equating them, like equate all the total heat of the various components entering to the various components exiting, and you are good to go. You don't need to memorize this formula. And now we can see from this formula that enthalpy is the common thing here. We have F multiplying HF, S is multiplying HS, and then V is multiplying HV, and then L is multiplying HL. So the question is, how do we get the various enthalpy values? Because in most questions, the figures for enthalpies would not be given to you. So you have to know how to get the enthalpy value and then use it for your calculation. And that is what I'm going to take you through right now. So the easiest way to do this is that for the feed and then the concentrated liquid product, we have a formula that we use specifically to calculate their enthalpies. But for the steam and then the water that is exiting as vapor from the upper chamber and then the saturated liquid, we get their various enthalpy values from the steam table, because literally they are all water. The steam is water, the vapor exiting from the upper chamber is water, and then the saturated liquid is also water. So we can just directly get their enthalpy values from the steam table, so we don't need to worry about them. But for the for the enthalpies of the incoming feed and then the liquid products, the concentrated liquid products, we can't get them from the steam table, so we need to calculate them. And we use this formula. For you to get the enthalpy of the feed, it is just a matter of multiplying the specific heat capacity of the feed by the temperature of the feed minus 0 degrees Celsius, which is a reference temperature. So when you fix in the values, you are good to go. CPF, that is the specific heat capacity of the incoming feed, is a constant, and normally it is given in the question, so you don't need to worry about that. And if you want to get the enthalpy of the concentrated liquid product, you just have to multiply the specific heat capacity of your exiting product by the temperature of the liquid product, which I said it is the same as the temperature of the chamber. It is the same as the temperature inside the chamber, which is T1. So you just fix in that temperature in there, and then you multiply by your constant, which is the CPL, and then you are good to go. So as I said, for the enthalpies of the incoming steam, the vapor exiting, and then the saturated liquid, we can directly get them from the steam table. So we don't need to worry about that. So this is how the steam table looks like. So you just have to look at the temperature given to you. So if, let's say, the temperature of the incoming feed, if the temperature of the incoming steam is, let's say, 60, you just have to check and then you read from saturated vapor column. When you look at this, let's look at this table. We have specific volume as one heading, and then we have internal energy as another heading, and then we have enthalpy in kilojoule per kilogram. So under enthalpy column, we have saturated liquid, and then we have saturated liquid here, and then we have the saturated vapor column as well. So they are all, These are all values that we can obtain, or like we can just get these values directly from the steam table and then use them for our respective calculations. So this is not a big deal. This is not something difficult that you should be worried about. You just have to get the values for saturated liquid, and then you get the values for the saturated vapor. The incoming steam is read from the saturated vapor column, whereas the exiting saturated liquid is read from the saturated liquid column. And for the exiting vapor through the upper compartment, we read it from the saturated vapor column. The only thing that we read from the saturated liquid column is the saturated liquid that is exiting. The steam that is rather exiting as a saturated liquid. That is the only thing that we read from the saturated liquid column. Aside that, any other thing is read from the saturated vapor column. So that is all I want you to take good note of. Now I can continue with the other calculations. So for the other calculations, we will be asked to also calculate the heat transfer rate, or we will be asked to calculate the heat transfer area. And this is the formula that we use. You can just fix in the values into this formula and then you are good to go. And you might also be asked to calculate your steam economy. And your steam economy is obtained by dividing your flow rate of the vapor by the flow rate of the incoming steam. So this measures the performance of your single effect evaporator system. You don't need to get a value that is greater than 1. When you get value greater than 1, it means that you are, when you get values greater than 1, it means that you are rather wasting the steam. You need to get very low ratio to show that indeed you are efficiently using steam for the production of your products. Now let's try this worked example. Before I start, please spend a few seconds to tap on the subscribe button for me and then like this video. Okay, so this is the question given. An evaporator is being used to concentrate potato juice from 11% total solids to 75% total solids. The juice enters the evaporator at a rate of 0.60 kilogram per second and the temperature of 40 degrees Celsius. The specific heat capacity of dilute juice and the concentrated product are 3.5 and then 2.1 kilojoule per kilogram degrees Celsius respectively. Steam inlet temperature is measured to be 120 degrees Celsius. The product inside the evaporator boils at 60 degrees Celsius. The overall heat transfer coefficient U of the evaporator is assumed to be 900 watts per meter degree Celsius. Determine A, mass flow rate of concentrated products, steam requirements, steam economy, and then the heat transfer area. So this is the question given to us, and then I'm going to take you through how to solve this question step by step. Now, step 1, we need to represent the information on the diagram. The question is too long, but we can simplify the question by using a diagram. So always draw this diagram and then fix in the various values. So we had these values from the question, and we just have to fix them to where each of them belong. When you are able to do this, you have solved the question for about 50%. This is the most important thing. The rest, you just have to deduce. You don't need to memorize any formula. Just deduce the rest from the diagram that you are having. So, the next step is to perform mass balance and then component balance. We can just get mass balance by using this formula. Mass in is equal to mass out, and we know that mass in is what? Feed and then the steam, and it should be equal to mass out, that is the vapor plus the saturated liquid vapor, and then saturated liquid and then the concentrated liquid product. So when we cancel out S and S, we're gonna get F is equal to V plus L. And from the question, we have F to be equal to 0.6 kilogram per second. And when we fix in the value here, we're going to get 0.6 is equal to V plus L. And this becomes our equation 1. Now, let's move on to perform component balance on solids. And as I said earlier, component balance is obtained by multiplying the fraction or the percentages of the components under consideration by their respective flow rate of the feed, the vapor, or any other products under consideration. And don't forget that the percentage of solids that we use to do the component balance calculation it is always converted to decimal. Don't leave it in a form of percentage, but rather convert it to decimal, and you are good to go. So we will get F multiplying 0.11 to be equal to V multiplying 0, and I hope you agree with me why V is multiplying 0. This is because YV, that is the percentage of solids in the vapor that is exiting through the upper chamber, is always given to be 0. So V will multiply 0 plus L multiplying 0.75. And when we perform this calculation, we're going to get L to be equal to 0.088 kilogram per second. Now we can confidently say that the flow rate of the concentrated product, the concentrated liquid product, is 0.088 kilogram per second. So let's fix in this value into equation 1 and then get the flow rate of the vapor that is exiting. And we're going to get V to be equal to 0.512 kilogram per second. And this is all for the mass balance and then the component balance. Now let's move on to step number 3. And this step states that we should perform energy balance. So we started by drawing a diagram. We perform mass balance and then component balance. And now we are performing energy balance. And by the time we will finish doing all these things, we will finish solving the question. So the energy balance is giving us the heat in to be equal to heat out. And we know the formula F, that is the flow rate of the feed, multiplying the heat content, that is the enthalpy F, enthalpy of the feed, plus the S, multiplying the enthalpy of the incoming steam, and it should be equal to the vapor, multiplying the enthalpy of the exiting vapor, plus the S, that is saturated liquid, multiplied by the enthalpy of the saturated liquid, plus the product L, multiplied by its flow rate, its enthalpy. So we need to calculate our HF and then the HL. We were not given these values in the question. We need to calculate it. And we know that HF is giving us CPF, that is the specific heat capacity of the incoming feed, multiplied by its temperature minus 0. And the question gave us CPF to be equal to 3.5. And this will multiply 40. That was the temperature of the feed that entered the chamber. So when we compute this, you're going to get 140.0 kilojoule per kilogram. And this is the enthalpy of the incoming feed. And let's do same for the product that is exiting. And when we do same, we're going to get HL to be equal to 2.1 multiplied by 60 minus 0. And we're going to get 126 kilojoule per kilogram. Now, for us to determine the enthalpies of the incoming steam and then the exiting saturated liquid as well as the product vapor, as well as the vapor that is exiting from the upper chamber, we need to use the steam table. From the steam table, we can determine the enthalpy of the saturated vapor at 60 degrees Celsius to be equal to 2609.9 kilojoule per kilogram. When you are reading from the steam table, pay close attention and then make sure that you are reading from the right column. So the vapor that is exiting from the upper chamber is exiting as a saturated vapor or saturated vapor. That is why we read from the saturated vapor column. So you just check the temperature and then you read from the respective column. And for the HS, that is the enthalpy of the incoming steam. We can obtain this at a temperature of 120 degrees Celsius. And the steam comes into the chamber as a saturated vapor. So we can get this to be equal to 2706.3 kilojoule per kilogram. And then lastly, the HS represents the saturated liquid that exited the chamber after the condensation of the steam. The steam condensed, and then after condensation, we are having a saturated liquid. So this is the only enthalpy that we would determine from the saturated liquid column. Aside this, all the other enthalpies are determined from the saturated vapor column. So we get it from the saturated liquid column to be equal to 503.71 kilojoule per kilogram. So now that we have the enthalpy values, we can then come back to the calculation and then fix in the values. So when we continue from here, let's substitute these values into the equation number 3 above here. So we have 0.6, that is the flow rate of feed F given in the question, and this multiplied by the enthalpy HF, which was calculated to be 140 kilojoule per kilogram, and this plus S, that is the flow rate of the incoming steam multiplied by the enthalpy HS, that is 2706.3, and this should be equal to 0.512. That was the value we got after calculating the flow rate of V, and this multiplied by 2609.9 plus S multiplying 503.71 plus 0.088 multiplying 126. So when you compute this and then you solve for S, you're gonna get S to be equal to 0.574 kilojoule per kilogram, and hence the steam requirement as required by the question is giving us 0.574. As simple as that. This is not difficult. You just have to know how to draw the diagram, and then the rest is so simple. Now, still on the solution, we are to calculate the heat transfer area. The question asked us to calculate the heat transfer area, and we have this formula stating that heat transfer area K is equal to UA multiplying TS minus T1, and this same formula is equal to S multiplying HS minus H small s. So you can use either of them to calculate for your heat transfer coefficient. The question needs the value of A, but looking at UA multiplying TS minus T1, when we equate this to SHS minus HS, we can straightly get our value for A. So let me first of all calculate for the value of Q and then equate it to the first side of the equation and then use it to calculate for A. So you can directly also fit in the values and then you will get your A. That will be very simple. You can just fix in the values of U, the values of TS, the values of T1, and equate it to the values of S multiplying HS minus small hs, and then you get your A from here. So I prefer to calculate for Q first, and then I equated this value to UA multiplying TS minus T1, and at the end I had my A to be equal to 0.0234 meter square. And then lastly, the question also required us to calculate for steam economy, and steam economy is obtained by dividing the flow rate of the exiting vapor by that of the incoming steam, and at the end we're gonna get the value to be equal to 0.892. This is a very good one. It is not more than 1. If the value is more than 1, it means that you are wasting steam to produce very few products. So we are done with the question. I want us to try one more question, because there are some instances whereby reading from the steam table will becoming so challenging, and this is because you might not get the exact enthalpy values for the temperature given to you in the question. Such values may not be read directly from the steam table, so you have to understand how to obtain such enthalpy values in case you can't read them directly from the steam table. That is why I decided to choose this example and then solve it together with you. So pause the video. You can pause the video and then try to solve it by yourself, and then you proceed watching it. And please, if you've not subscribed yet, kindly support me by subscribing. Thank you so much. That is the only way you can help me. Yeah, thank you very much. Okay, so let's continue with the calculation. As I said, the first thing to do is to draw a diagram to represent the information. And from the question, these are the values that we got for feed S. These are the values that we got for the feed, the temperature F, XF, and then etc. These are the values that we got from the question. So you just have to fix them in here. And yes, we have represented the information on the diagram. And then the next thing to do is to perform mass balance and then component balance. And we know mass in to be equal to mass out, and F plus S to be equal to V plus S plus L. And when we fix in the values, we're gonna get our L to be equal to 0.088 kilogram per second. And we can fix this into equation 1 and then calculate for V to be 0.582, and we are good to go. And then the next step is to calculate your energy, or to perform your energy balance. And this is the formula that we have: FHF plus SHS to be equal to VHV plus SHS plus LHL. And we need to calculate for HL and then HF by using this formula for enthalpy. And we're going to get HF to be 168.87 kilojoule per kilogram, and then our HL to be 143.06 kilojoule per kilogram. And then lastly, we can determine HS and then HV from the steam table. So HV, the temperature that we are to determine the enthalpy, is given to be 62.2 degrees Celsius. And looking at the steam table, we can't directly get 62.2 from here. We can't get it directly from here. So how are you going to get it? We can get it by by extrapolate or like interpolating it between 60 and then 65. We know 62 to be in between 60 and then 65. So we have to get from this steam table that we have HV, like we have the value of we have the enthalpy of saturated vapor at 60 degrees Celsius from the steam table to be 2609.6, and then the enthalpy of the saturated vapor at 62.2 is what we are looking for. We don't know. And then lastly, the HV represents the enthalpy of the saturated vapor at 65 degrees Celsius. So now that we have these three figures, we can then use them to work out for our enthalpy at 62 degrees Celsius. So this is the formula that we use. T2 minus T1 over T3 minus T2 should be equal to H2 minus H1 over H3 minus H2. So H1, I just assume that the least value or like the least temperature value among them is our H1, then the middle one or like the middle value becomes our H2, and then the highest value becomes our H3. So in this case, 60 degrees Celsius will represent our T1, 62.2 that we are looking for would become our T2, and then lastly 65 degrees Celsius, which is the highest, would represent our T3. So when we fix in the values in there and then we work out for H2, we're gonna get H2 to be equal to 2613.43 kilojoule per kilogram. And then the question also gave us the values of saturated vapor pressure to be equal, saturated vapor to be 0.3130 kilopascal. So we can directly get this from the steam table. And then HS2 can be gotten directly from the steam table as 567.69 kilojoule per kilogram. Take note that it is not always that the question will give you the temperature inside the it is not always that the question will give you the temperature of the incoming steam, but it would rather give you the vapor pressure of it. So when you are given the vapor pressure, just use that value. You can get that value. You can get a column for your vapor pressure from the steam table. So the 0.3130 corresponds to 135 degrees Celsius. So you just use it to work out for your various values for the enthalpies of the saturated vapor and then that of the saturated liquid. So after getting these values, you can then feel free to fix them into your equation 3 here, and then you work out for your S. And we are good to go. And at the end of the day, the steam requirement would be 0.71 kilogram per second. So this is basically how we perform calculation on single effect evaporator system. I've given you this trial question. Try this out. When you finish, you can comment with your answer and then I'll check out for you. Thank you very much for watching the video to the end, and don't forget to subscribe for amazing content. Thank you. See you another time.